Today we're looking at elliptical orbits. All right, so if the moon ran around the Earth in a perfect circle, then the moon would always appear to be the exact same size. We know this is not true because sometimes the moon is larger and sometimes it is smaller, or it appears to be. That is because the moon goes around the Earth and the Earth goes around the sun in an oval, or what is called an elliptical orbit. One thing you should probably do is highlight that, make it bold, elliptical, okay? And as you can see right here, you've got us going around the sun in an ovalish, and the moon going around us, ovalish. As you can see, in our orbit around the sun, sometimes we are closer, like right here, and sometimes we are farther away. With a big object like the sun, its gravitational pull, when we're closer, we are moving faster. And one of the things you should notice, let me move myself, is when we're closest, we're perihelion, and when we're away, we're aphelion. Very important things to remember. I think I already went over this before. Perihelion is closer, or closer to the sun. Helium, closest, and then aphelion, away. All right. Eccentricity, that I have put in bold for you because you've got elliptical and eccentricity, both these things. So elliptical is what shape the orbit is, like how we're going around, and eccentricity is that measurement of how oval an elliptical orbit is. So elliptical orbit is going around that circular-ish shape. And eccentricity is that number that can tell us what the actual shape looks like. And so the formula in front of your reference table, page 1, again, reference table, necessary tool in this class. If you look over here in the equations right here, it says eccentricity. It has the distance in between the foci over the length of the major axis. What it means is the 2 points, the distance between the 2 points, here's a hint, it's always smaller than the length of the major axis. That just means the longest distance apart. So there's the longest, you measure that, that is always going to be larger than in between the foci. So in this elliptical orbit, let's move you right there. One of the foci is the sun. So in ours, it's always going to be the sun. The other is an imaginary point in space. It could be a planet. It could be an asteroid. It could be any of those. So the length of the major axis is the distance all the way across the ellipse. What is moving around the orbit in the sun could be a planet, comet, or asteroid. Eccentricity is a number between 0, which is a perfect circle. How to remember that? Well, 0 is a circle. And, let's move me, 1, which is a line. 1, if you were to just draw 1, it'd be a line. So you've got 0, a circle, 1, a line. It's more eccentric the closer it becomes to a line, okay? So it's less eccentric at a 0, more eccentric at a 1. How the heck do you draw this thing? So if you were in class, I would have you actually draw some ellipses. Because you're not, you're going to just get to see how to do it. So how do you draw it? Well, look above. What you would do is you would have 2 tacks, and one is the foci 1 and one is the foci 2. So one would be like the sun, the other one would be like Earth. One focus represents the sun and the other an imaginary point. The major axis is just the distance all the way across the ellipse or all the way across the oval. So you have the foci. This one's a little bit different. You'll see that in the odd puzzle today, where they just have it wrapped around 2 pins and then going around like that. You can do that, or you can have a string. Either way. So let's do a little problem. All right. You may need a calculator, your cell phone at this point in time. So say the distance between the foci, the top part, is 2, and the length all the way across is 10. What is the eccentricity of the ellipse? Again, you're going to take the distance between the foci over the longer distance. So you're going to have 2 over 10. So if you're to type that in, 2 divided by 10 equals 0.2. So, and here's the thing. There is no units for this. So for those of you who haven't been giving me units, this is a bonus. There are no units. All right. So we're going to look up some eccentricities. I'll move me to where I'm like out of the way. Right there. All right. So we're going to look them up. How do you look these eccentricities up, Miss Co? Page 15 of your reference table. You're going to see the eccentricity of orbit. So looking up these numbers, Mercury, you're going to find, has an eccentricity of 0.206. For Venus, it's 0.007. For Earth, it's 0.017. For Mars, it's 0.093. Based on these numbers, with the most elliptical or oval orbit is Mercury, because the number is closest to 1. So because that is really, really close to 1, it's going to be the most elliptical. Well, let's look and see. You see how it's got that tilt right there? Oh, that's Mercury. Yes, Mercury has that tilt. Yes, it's definitely more elliptical. And the planet with the least elliptical orbit, or most circular, is going to be Venus, because that's a 0.007. Why? Because the number is closer to 0. So 0 circular, 1 elliptical, most oval line. All right. Well, let's do a little application. What if an asteroid in our solar system, which I think there's one coming towards us at this point, has a highly elliptical orbit and crosses the Earth's orbit, which is fairly circular. So what's going to happen? Where could it hit us? Well, if that's the little object, it could hit us here, 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 or here. There are 4 places it could hit us. Kind of crazy, huh? If it's fairly circular, it could hit us in 4 different places. Okay, so that's it for today. Make sure to watch the Edpuzzle. Hop on Zoom. Ask any questions if you need them. Definitely hop on Zoom. And I will see you later.